Welcome back. Today I will talk about the Perceptron, and later we have to think about how we can use Python to make this algorithm useful in a machine learning context. So first, it's quite nice to scribble a little bit and just to work around the equations and try to understand actually what these equations are doing. Now, first of all, it's important to note that our main aim, our task, so to speak, is to classify observations, and we have to assign an output which we call y. Just put this down here, y hat. And this output could be either +1 or -1. Now, what this +1, -1 actually really means is not really relevant. It could be, for instance, whether a company goes into default or not. It could be a classification for someone using a particular mode of transport, yes, no. It could be anything else. Good. And what we do is we look at this output, which we call our classification, and we compare that to our actual classification, which is given in our training data set. So it's important to note that we have two different data sets. We have our training data, which gives us an opportunity to learn. Based on the training data, we will be able to derive what is called a decision boundary. Once we have a decision boundary, we can then classify data where we know nothing about the true output. So that is the idea. Yeah, we have a training data set. We learn from the training data set. Once we have a good rule discovered, which we call a decision boundary, once that is discovered, we can use it to classify unseen data, just by knowing the so-called inputs. So what do we know? It's a good point to make. So actually, what is known in our case? So what we actually do know is we know we have so-called inputs. Now I use the language used in machine learning. So if you come from a statistics background or from an econometrics background, you would call these inputs also variables, or you could call them covariates, you can call them explanatory variables. And these inputs are written as a vector, and if I write a vector, I always underline the vector, I underscore that, because I can't easily do bold. So if you are in print, of course you would just do bold, but here, writing it out, I always use an underscore to indicate that this is a vector. And we would refer to this as a column vector, starting from a particular input 1 and going up to an input m. Yeah, so here we have not 1, we have m inputs which we can observe. Okay, so that is the starting point. In our training data set, we also know the true output for each and every individual. So that is known as well. Now the true output, we call this y. So when we look into our training data, we do know y. So y is known as well. Yeah. Of course, once we go outside our training data, that does not apply anymore. Good. Now the next thing to note is we have weights and we have a so-called net input. Now the weights basically take my inputs and apply a particular weight to each and every input. So when it comes to the weights, it's again a vector, which I just put down next here. And this vector, again a column vector, starts with W1 and it goes all the way up to Wm. So for each and every input m, we have these different weights. When you start the algorithm, the weights are set at a particular level. Usually you would just select these weights randomly before you start learning from the data. In our example, we just set these weights equal to 0, but of course that's entirely random. It's decided by us. Next, what we need is a so-called net input, and I put here usefully maybe a definition, and I want to define what is called a net input, which is denoted set. And you note that the set input is actually a scalar, which means it's simply a number, it's not a vector anymore. So what it does is it takes all these inputs and the associated weights and adds them up. Yeah, so basically this is the operation done by the net input. Yes, it's a weighted sum of all the inputs. Now, if we go back to lecture 1 and we talk about standard matrix operations, you can also write the same using a matrix notation. You can take the vector of weights, you transpose it, so you just put a little prime here or a t, both is used. You take the transposed vector, which now becomes a row vector of dimension 1 times m. Yeah, so you have one row, you have m columns, times x vector, which is m times 1. You see these dimensions match, so the outcome will be 1 times 1, which is of course a scalar, which is my net input. Is exactly the same what you see on the first line. Another way of writing this is to use the dot product. Again, we have done this before, which is w times, using a dot product, x. So note here the dot product is indicated using this multiply sign, which is not multiplication in the normal sense. Yeah, this is a dot product multiplication, which means you take the first item in the vector w, you multiply the first item in the vector x, and then you add the next items multiplied. So exactly you obtain what you see on the first line. Okay, so that is what we call a net input. Now the interesting thing is how this net input then translates into our classification. So how do we move from our net input set to y hat, which is our output or our classification? And what we do here is we basically define what you might call a trigger. So that's a trigger, or mathematically speaking, it's a so-called heaviside function. Let's put that down. Heaviside. Some people also call this a heaviside step function, which basically assigns a certain value depending on the value of the net input. Yeah, so I call this phi, which is a function that depends on set. There are two outcomes here, either +1, -1, if set is larger equal to a theta, and if set is less than theta. Yeah, so this is basically the classification rule. Now theta is a level which we don't know initially, and it's basically what you might describe as a threshold level, which is not known at the beginning. Now it is a common convention in this algorithm to in fact set the threshold equal to 0 and this is done using a so-called bias unit. A bias unit is an additional input which you include in your model, which simply takes the value x0 equal to 1. Now this actually is like a constant term. So if you have done some statistics in the past and you have done some regression models, you know that if you take the value 1 throughout, you actually get a constant term, and you have an associated weight which is simply minus theta. Yeah? So that would basically remove my threshold. So if you go back to this equation here, if you add on the right hand side the minus theta times the x0, yeah, you would add it here, then it neutralizes the threshold z has to climb, and the threshold actually then becomes equal to 0. Yeah, so put differently, if you want to decide whether you are +1 -1, you basically just look at this equation here, you add your bias unit, and then you just ask yourself whether it's larger or equal to 0 or less than 0. So that's then the decision rule. Okay. Now basically, following that argument, you obtain what is called a decision boundary, which refers to your set your net input equal to 0. Yeah, so that is basically, in our setting, it would be in a two-dimensional case, and I just will make this example in a minute. That would be a straight line in 2 dimensions. Of course, if you go into higher dimensions, it's actually a plane. Alright, so that is our initial setting. Okay, that's useful. Now I just move this a little bit further up. I have to be a bit careful. So here we go. So now what we need to do next is we have to think about our decision rule, or our learning in this algorithm. First, let me introduce a parameter which are called eta. So that's eta, it's a Greek letter, which is also called a learning rate. So the eta actually tells you how much you adjust if you are wrong. If eta is large, it would lead to a quicker resolution to the correct decision boundary. However, if you make it too large, you might overcorrect. So there is a trade-off between setting eta too small, which means you have very, very little adjustment, or setting eta too large. So both can be problematic. Now, the learning rule in the perceptron goes as follows: delta wj is equal to eta yi minus yi hat times xij. Now that is our rule for adjusting the weights. Now this looks a little bit like mumbo jumbo for most of you, I suppose, but actually it is quite straightforward. So if you think about this, it means the following: the delta refers to a change. There's a change of weights. Again, note we have j running from 1 up to m, different inputs and different weights, and we have I running from 1 to up to capital N observations. This might refer to individuals, it could be firms, it could be anything. So looking at that, it basically tells me adjust my weight. Now I have to be a little bit more precise here. I actually also have to include 0, which is my bias unit here. That would be more precise. So adjust my weight if you are wrong. So again, note that this is my output here, the y hat. That is the observed y in my training data. So if I predict a +1, but actually -1 is true, you obtain -1, which gives -2 times my learning rate times my input, which adjusts the respective weight. So that is the rule. Now it is really useful also for implementation to work through a very small example and just see how this actually works in practice. Okay, I do a very simple example. So that I think is always a good start, also when you later want to develop your own algorithm. It's a very good start to think about a very simple example. Let me just move this a little bit further. Okay, so what I do is I simply refer to 3 different cases. So we have 3 cases. Now the cases would be I is equal to 1, 2, 3. So we have, say, 3 individuals or 3 firms or anything else you could imagine. So that would be my cases. Then we have only 2 actual inputs. Of course we still have our bias unit, but we have 2 dimensions here. So we have j is equal to 1, 2. So that would be my initial setting. And in terms of how the data look like, I can have a data matrix. So this would be captured in a matrix, or later, of course, when we move into Python, we would call this an array, where we put our information into a certain structure. I now use my ruler just to make sure it doesn't look too rubbish, to make it easier to actually read this properly. So here we go. So we have here our first case, we have our second case, we have our third case. So here I put my cases. So we have basically how many rows do we have? We have n, capital N rows, depending on how many cases we have in our data. Then here we have the x0, which is our base, x1, x2. So that is our constant term. Then we have our y, which is the observed actual classification, which we know in this case because we are in our training data. Let me just do that to make it look a little bit more pretty. Now the first observation, of course, gets a base of 1. Everyone gets a base of 1 because that's the constant term. Now the first observation has a value of 2 in x1, value of 1. No, let me just change that. Value of 1 works better this way. Value of 1 in x1 and a value of 2 here, and we have a +1. Then we have a 2 and a 4 and a 3 and a 1, and here we have a +1, -1. Now this is honestly arbitrary, it doesn't really matter. It's also useful to actually visualize this in a little figure. Of course, in 2 dimensions you can still handle it. In higher dimensions I would not bother, because then of course you're running out of things you can visualize. Okay, so we do this now for x1 and x2, and we go up to 4. So let me just put a ruler here so that we are more or less right. 1, 2, 3, 4. So we need that 1, 2, 3, 4, and we go up here by 4 as well. Okay, and then we just simply plot our data. So the first case, we have here a 1, we have here a 2. You can ignore the constant term. That does not matter because that's just our adjustment, our base unit. So we are up here. Yeah, so 1, 2, we are up here. So that's 1. And that is a +1. So I use the notation solid dot is +1 and empty 1 is -1. So that is basically here my y. So that is my actual classification based on my training data. So when I go to number 2 and number 4, so I'm somewhere up here, again this is also +1, so that's my second observation. Then my third observation is now a 3 and a 1, it's here, so that's my third observation. Good. Now, of course, we kind of intuitively know that we could separate these cases just by putting a line somewhere here. Yeah, we don't, of course, know exactly where the line should be, and in fact, this algorithm does not always create a unique line. In fact, it usually never does create a unique line, but that depends on the number of observations you have. So somewhere here there must be a separation going on. Yeah, somewhere here. I think we should be able to separate them. Now, how does this algorithm work? We have a starting value for the weights. I randomly select that all the weights are equal to 0. But of course that's entirely up to me to do. Now if all the weights are equal to 0, obviously we know that by definition in our first round z is equal to 0. If z is equal to 0, going back to our Heaviside function, it would classify in my first round all of these cases as +1. Yeah, so we go through this. If you have y hat, and I just put here 1 in brackets up, which is a notation common in numerical methods, so that is our first iteration through the data, we would get the following. So the first observation would be classified as +1 because z is positive, is equal to 0. So based on that, looking at my adjustment, the prediction is 1, the actual value is 1, so that's 1 minus 1 is equal to 0, so actually the weight is not adjusted. But when we go to the next observation, again I would predict 1, which is true, so there is no weight adjustment. Then we go to the last observation, but here I would predict 1, but the true value is actually -1, so here you get an adjustment. And now you simply have to go through the learning rule. Yeah? The initial weights are all equal to 0, so basically the change in weight is equal to the new weight, yeah, because the initial weight is equal to 0. So based on the equation, you could easily write down W0 is equal to the eta, which we have to set. I just put it down here. We can, for instance, use, that's up to us, eta equal to 0.5. Let's use that. So we have 0.5. We go into our brackets here, and we have our actual value, which is a -1, minus our prediction, it's another -1, times now the x0 for the third observation. Now x0 is always 1, so this is what it is. So we obtain here -2, I get a -1, and then I have a W1 here, which is also 0.5, and again we have -1, -1, and we have the value now of x1 on the third case is equal to 3, so we get a -3, and we have a W2 which is 0.5, again -1, -1, and we are here in times 1, that's this case here, and we get a -1. So in this third case, in our first run through our data, we would then get the following. I just pop this over here. We would get the following. We would get z is equal to, now we have our bias unit as simply -1. Yeah, that's -1. x0 is always 1, so I can just drop that. Then we have -3 x1 and -x2. Yeah, so that is basically my decision boundary. Now if we want to plot this, we of course can set this equal to 0, because we have our bias unit adjustment, and we can of course, solve this for x2, which we always do in 2 dimensions. So I put it on the other side, I get -1 minus 3x1, so that would be my decision boundary. So if you want to plot this, this decision boundary is somewhere on that side. It has an intercept of -1, and then it drops by -3 for every move you make, so you're somewhere down here. Yeah, so it's hard to plot here. Let me just put this here. It would be somewhere running here. So that would be my decision boundary. Now, this decision boundary, of course, is quite useless. It's not correct, obviously, and then we would go into the next round. And now, based on this rule here, our net input would be, of course, for the first observation now negative, which means it would be wrongly classified. And then you would have to readjust these weights, and so on and so on. So that is basically how this algorithm works. That's a nice example. So what we do next is we try now to use our skills in Python to implement that, because obviously doing this by hand doesn't really make too much fun. It becomes very boring at one point, so we now use our computing power. That's all for today. I'll see you in the next one.